So we are starting module 5 today. So that is about greedy method. Greedy method is again an algorithm design technique. Okay. Another algorithm design technique. So here, in the case of a greedy algorithm, normally we'll have a set of n inputs. Okay. Then output is actually we need to find out a subset of this input which satisfies some constraints. So we have a set of n inputs and we have certain constraints on this input. So we'll choose a subset of these inputs which satisfies these constraints. Okay, any subset that satisfies these constraints is known as a feasible solution, and we need to find a feasible solution that maximizes or minimizes the given objective function. Okay, so that kind of solutions are known as optimal solutions. Okay, so greedy algorithms are typically used for this kind of minimization, maximization problems, or we can say that optimization problems. Okay, and which means there will be an objective function, and our aim is to maximize or minimize the objective function. Okay, and any feasible solution that does this, that is known as an optimal solution. So which means the greedy algorithm actually works in stages. Okay, and it considers one input at a time. Understand? Okay, it considers actually greedy algorithms എനിക്ക് എന്തോ റിക്വസ്റ്റ് വരുന്നുണ്ടെന്നാണ്. Okay. So greedy algorithms actually work in stages. So at each stage, a decision is made whether a particular input is in an optimal solution or not. Okay. So which means we'll consider these inputs in an order determined by some selection procedure. Okay. And will determine whether inclusion of this or inclusion of the next input into the partially constructed solution, optimal solution, will result in an infeasible solution. So our aim is that we have a selection procedure. We first will order the inputs in some manner that is determined by the selection procedure, and then we'll choose or we'll pick one input at a time, and we'll decide whether this, if inclusion of this input will lead to an infeasible solution. If so, then that input will be discarded. Otherwise, that will be a clear solution. Okay. So input is there. You just need to find out subset of this input, which is your output. Okay. So you'll decide whether inclusion of the next input will lead to an infeasible solution. We at each stage we are constructing the output. For that, we are considering one input at a time, and we'll check whether this will lead to an infeasible solution. Okay, that is the case. And we can say that the selection procedure is actually based on some optimization measure. Which means optimization measure means that maybe selection is based on we need to maximize something or minimize something. Okay. Then, and this measure, that is the optimization measure, that is known as the objective function. Okay. And several different objective or optimization measures are plausible for a given input. And most of this will result in algorithms then that generate suboptimal solutions also. And this version of the greedy technique is known as a subset paradigm, which means we are actually constructing a subset. And we can actually define a control abstraction for this kind of greedy algorithms. So your algorithm is like this: algorithm greedy a comma n, and a is actually your array, and n is your number of inputs. Okay. So a of 1 to n contains n inputs. Then we are trying to find out the solution. So at each step, we are trying to find out whether one particular input can be included or not. Okay. So for that, we are setting or initializing this solution as the null set. Then for I is equal to 1 to n, do that is for each input, we'll first x equal to selectify. We'll select one input, okay, and this we need to define how to select this based on some selection procedure. Okay, this we need to define. Select. Then if feasible, then we'll check we have selected A, which means one input from A that we can call as X, and we are checking whether if feasible of solution from X, which means if we are, this is our partially constructed optimal solution, and whether adding this X will lead to a feasible solution. Okay, that's what we are checking. And if this condition is true, then we'll set solution as unit of solution from x, which means x will be added to the solution. Otherwise, we'll pick the next input, etc. Until then, we'll do this, and finally, we'll return the solution. Okay, that is our control abstraction. This is how a greedy algorithm works. The first greedy problem as a knapsack problem. Okay, so we have actually knapsack problem is there in your syllabus, then Prim's algorithm, Pascal's algorithm. So knapsack is the first one, and Prim's and Pascal's I will give you as a self study. Okay, so here knapsack, in this we are considering actually a fractional knapsack problem. This you can call as a, because a knapsack problem has two variants. One is a fractional knapsack problem, another one is a 0-1 knapsack problem. There the fractions are not allowed, either the input is taken or not taken. So in the case of a fractional knapsack problem, you can take a fraction of the input. Okay, that's why it is a fractional knapsack problem. So in a typical knapsack problem, you have n objects and a knapsack. So this object I, we have n inputs or n objects, and each of this object has a weight wi. So you can call that object I has a weight wi, and the knapsack has a capacity m, which means knapsack can contain only some objects which has, for example, weight m kg. Okay. So that is weight. So we have n objects, and object I has weight wi, and a knapsack has a capacity m. If a fraction xi, consider a fraction xi, this one is xi. Okay, 0 less than or equal to xi greater than or equal to 1. Of object I is placed into the knapsack, then a profit of Pa into xi is earned. So it means that each object has some profit associated with it. When you pick one object, which means you will get some profit. Okay, you can call that profit as actually Pi. For I object, the profit is Pi. So here we are choosing a fraction of the input. Okay, and this fraction you can define as, which means xi is in between 0 and 1. Then if you pick this fraction xi of object I is placed into the knapsack, then you will get a profit of Pi into xi. That is clear. Okay, you will get this kind of this much profit. Then the objective is to obtain a filling of the knapsack that maximizes the total profit in. Okay, so our aim is to maximize the profit. So we need to fill the knapsack. So our capacity is m. So you need to fill this knapsack with all the subjects, but you should choose these subjects in such a way that your profit is the maximum. Okay. Since the knapsack capacity is m, we require the total weight of all chosen objects to be at most m. That is the case. Okay. Because a knapsack has a capacity that is m, so we cannot take objects which has more weight when compared to this n. Okay, which means simply we can formally state this problem as to maximize sigma pa into xi, where I ranges from 1 to n. Okay, our aim is to maximize the profit, and that profit is pa into xi, and subject to the condition sigma Wixi should be less than or equal to n, where again I ranges from 1 to n. Okay, so Wi into xi, what does that mean? Each object has weight, each object I has weight Wi, and if we are taking a fraction of this object xi, then your weight will be Wi into xi. Okay, and you should okay. Then you should multiply these two, and you should add this with all Wixi, where I ranges from 1 to n. And your conditions are this: 0 less than or equal to xi less than or equal to 1, and 1 less than or equal to I less than or equal to n. And we are assuming that the profits and weights are positive numbers. Okay, the profits and weights are positive numbers. So your knapsack problem is actually to maximize pa into xi, summation of pa into xi, subject to this condition, that is capacity of this knapsack is n. So you should choose this objects in such a way that sigma Wixi should be less than or equal to n, and your xi ranges from 0 to 1, that is a fraction, and I ranges from 1 to n, where there are n inputs. And a feasible solution or filling is any set x1, x2, etc., xn satisfying the second and third above. Okay, so a feasible solution means a feasible solution. The feasible solution means you should find out, or you should get a filling of this knapsack. Okay, and you are subject to these two conditions only when we talk about a feasible solution. I'm going to wait here. Request remember. Okay, so any set x1 to xn which satisfies these two conditions. Okay, the second condition and third condition, and that is known as a feasible solution, which means you are trying to find out a filling of the knapsack. When you get a filling of the knapsack, that is your feasible solution. But your optimal solution means you should satisfy your first condition. So which means you should find out a filling which maximizes this value. Okay, so an optimal solution is actually a feasible solution for which the first condition is maximum. Okay, if it is a maximum, then you can say that that is an optimal solution. Consider an example, that is n is equal to 3 and m is equal to 20, and your profits P1, P2, P3 for x1, x2, x3. You can say that there are three objects and the capacity of your knapsack is 20. So P1, P2, P3, that is 25, 24, then 15, and W1, W2, W3. That is your weights of each objects. That is 18, 15, 10. Then Some feasible solutions are listed here. That is, four feasible solutions are here. So you have x1, x2, x3. That is your fractions for the first input, second, and third. And this is your sum of wi into xi. This is sum of pi into xi. Okay. So the first condition, first feasible solution is x1 is 1 by 2, x2 is 1 by 3, x3 is 1 by 4. Okay, randomly some feasible solutions are given. Okay, some feasible solution means you are trying to find out what the filling of this knapsack, and the capacity of this knapsack is 20. So you should list out all this, all the inputs or all the solutions which satisfy these two conditions. Okay, where your weight should be less than or equal to m, and your xi and 1 should be like this. Okay, so you can say that this one is a feasible solution even though sigma WAXI is 16.1, where that is less than or equal to 20. So you can choose this one, and your profit sigma PI into XI, that is 24.25. Okay, then the second case is you are picking 1 comma 2 by 15 comma 0. There it is 20 and its profit is 28.2. Then another case where your weight is 20 and profit is 31. Then 0, 1, 1 by 2. Then 20 is 31.5. And we know that the fourth one will actually gives the maximum profit. In this, out of these four solutions, this one yields the maximum profit. Okay, in case the sum of all the weights is less than or equal to m, then clearly xi is equal to 1. Suppose you have n objects again. Then suppose sum of all these weights is less than or equal to m. Okay. In that case, you can clearly say that xi, that fraction is 1 for all n. Okay, 1, sorry, for all I. 1 less than or equal to I less than or equal to n is an optimal solution. Okay, because your total weight is always less than or equal to n. So let us assume the sum of weights exceeds m. Suppose sum of weights exceeds m. In that case, xi's, all the xi's cannot be 1, because all the fractions, all these objects should not be taken. Okay. Then another observation to make is that all optimal solutions will fill the knapsack exactly. This is true because we can always increase by a fractional amount the contribution of some object I until the total weight is exactly m. So we can say that there are two observations. One is that if sum of all weights is less than or equal to m, then all of these objects can be taken and xi is equal to 1, and that is an optimal solution. And suppose this sum of all these objects exceeds m. In that case, xi cannot be 1, but all optimal solutions will fill the knapsack exactly, because this sum exceeds n. So anyway, all optimal solutions will fill the knapsack exactly, because we have the provision to take fraction of this input. Okay. So we can always increase by a fractional amount the contribution some object I until the total weight is exactly m. So that is clear now. Actually, the greedy method is, first we may try to fill the knapsack by including next the object with the largest profit. Next object with the largest profit. Then if an object under consideration doesn't fit, then a fraction of it is included to fill the knapsack. Okay. Thus each time an object is included, except possibly when the last object is included into the knapsack, we obtain the largest possible increase in profit value. Note that if only a fraction of the last object is included, then it may be possible to get bigger increase by using a different object. So we'll see all this thing. For example, if we have 2 units of space left and 2 objects with Pi is equal to 4, Wi equal to 4, and Pj equal to 3, Wj equal to 2 remaining, then using j is better than using half of I. Okay, because when you take half of this Wi, you will get profit 4 only. But if you take j, weight is 2 and you will get profit 3. So that's called sometimes, okay, if only a fraction of the last object is included, then it may be possible to get a bigger increase by using a different object. You should find out all these cases. Then there are some lemma. This is what we discussed just now. In case the sum of all weights is less than or equal to n, then xi is equal to 1 and I ranges from 1 to n is an optimal solution. That's what we said. Then sum of weights exceeds m. Now all the xi's can't be 1. So another observation means all optimal solutions will fill the knapsack exactly, because we have the provision to take a fractional knapsack, and that is the fraction of the input. That is the main attraction of this fraction knapsack, where you have, if you have a 0-1 knapsack problem, then either you can take an object or you cannot take it. You cannot take a fraction of the object. There sometimes you will get an optimal solution where the knapsack is not full. Okay, that is not full. And then we know that first step is actually try to order this input based on a selection procedure. Okay, how you can select, or you can pick a selection procedure. It is your ordering of the input. Anyway, your aim is to fill the knapsack with maximum profit. So what are the different selection procedures you can choose? Suppose you are sorting this input in the order of non-increasing profit. Okay. So you are sorting your input first in the order of non-increasing profit. You can try that. Okay. You can sort your input in non-increasing profit. Then choose objects in this order to maximize the profit. Because non-increasing profit means your sorted order will be the object with maximum profit will come first and second, etc. Okay, so you will get, if you take input in that order, then you will get maximum profit. Okay, so for example, again with the same input 25, 24, 15, non-decreasing, it is not non-decreasing, it is non-increasing. Okay, should be non-increasing, right? It is a mistake. Non-increasing order of profit, then you can pick 1 comma, so it means your profit is 24, then 2 by 5 comma 0, 1 comma 2 by 5 comma 0, which means your solution is 1 comma 2 by 5. You'll pick the first one, that is, I think that 25 is the first object, 24 is the second object, 15 is the third object, profit of the third object. So you can choose the first object that is that has the maximum profit. So this is actually in non-increasing order of their profit. Sorting this object or set of objects in non-increasing order of their profit. So you get 25, 24, comma 15. Okay. So that is the actual order. Then you can choose objects with profits 1 comma fractions 1 comma. The first object is taken full, then the second object 2 by 5 of the second object is taken. Then you get the maximum profit. Okay, that is 2 by 5 minus 0. I think the solution is here. There is a 1 comma, I think 2 by 5 can be written 2 by 15. Okay. 1 2 by 15, is that correct? Because the first object is 18, yes, 2 by 15. Then you'll get 2 here, so your total will be 20. Okay. So which means 2 by 15 is your condition, which means this one is your solution. 1 comma 2 by 15 comma 0. Okay, so 1 comma 2 by 15 comma 0, that will give you a solution. Okay, so 1 comma 2 by 15 comma 0, that is by sorting your input in non-increasing order of their profit. So you'll get capacity 20, or their total weight is 20, but your profit is 28.2. Okay, that is not your maximum profit. Okay, so which means if you choose non-increasing out of their profit as your selection procedure, it will not give you a maximum profit. Okay, that is the observation. Then what we can do, we'll try another observation, that is non-decreasing order of the weights. Okay, so you can order this input in non-decreasing order of their weights. Okay, so if you order this inputs like this, then choose maximum objects with largest weights. So what will happen? Your solution 3 is so you must sort your objects in non-decreasing order of their weights. So you'll get first object, or in first place you'll get the third object, then your second object, and your third object. Okay, so 10 15. So 10 15 and 18, that is your order. You are ordering it as W3, W2, W1. Okay, then you will pick the first one, that is 10. So which means the third object will be taken. Okay, third object, this thing will be taken fully, and the second object is actually 2 by 3 of the second object will be taken. 2 by 3 there, and the third, which means the first object will be discarded. And if you go like this, you'll get profit of total weight is 20, and you'll get a profit of 31. Okay, that is again not an optimal solution, because we got an optimal solution where the profit is 31.5. So this one will actually not give you an optimal solution. Then what we can do is that we are actually considering a ratio between profit and weight. Okay, because we are taking fractions of input, it is fair to use the ratio between the profit and weight. Okay. That is, we are calculating PI by WI, and we'll sort this input in non-increasing order of PI by WI. Okay, so you should find out, or you should calculate PI by WI for each object, and you should sort the objects in non-increasing order of PI by WI, and that will give you an optimal solution. Let's check that. So PI by W. Compute PI by W. 25 by 18, 24 by 15, then 15 by 10. So when you sort them, the second object will come first, then third, and fourth will come last. Okay. So try to find out PI by WI. PI by WI, the second object will come first. So you'll choose a second object fully, then the third object will be, half of the third object will be taken, and your knapsack will be full now, and you'll get a profit of 31.5. Okay, so clear. So we are talking about the selection procedure. The selection procedure is actually that goes with the optimization measure. So for example, when you choose the selection procedure, it should give you, or it should maximize the objective function. Okay, that is the way. So we are trying to find out some selection procedures in the case of a knapsack problem. Suppose we are sorting the inputs in non-increasing order of profit, and we have done that, and we'll choose objects in this order to maximize the profit. And we came to know that this will not yield an optimal solution. Okay, and now we take another ordering, that is order. We are sorting the input in non-decreasing order of weights, and we are choosing maximum objects with the largest weight. Okay, and that will actually not give you an optimal solution. So we are trying to find out a ratio between profit and weight, and we will sort them in non-increasing order. Okay, you have found out the ratio between profit and weight, that is PI by WI, and you are trying to sort them in non-increasing order of PI by WI, and that actually will give you an optimal solution. ഇതെല്ലാം ചെയ്ത് നോക്കുക. And this is your okay algorithm: greedy, knapsack, m comma n. So sort profit weight ratio PI by WI in this ratio, and this should be greater than or equal to PI plus 1 by WI plus 1. Okay, that is and by non-increasing order of their ratio. PI by WI is greater than or equal to PI plus 1 by WI plus 1. Then your solution is this array x of 1 to n, small x. Okay, small x of 1 to n is a solution. For I is equal to 1 to n, initially we are setting this output array as 0. This output array will give you the fraction of the input, that is 0.0. Then you are setting u as n, where m is capacity of the knapsack. Okay, that you can call as u. Then for I is equal to 1 to n, if that is you are picking each input and checking whether that is a feasible or not feasible. So if Wi is greater than u, then break, which is Wi is your weight, and if you are picking one input and if Wi is greater than u, then you will break. Otherwise, x of I is equal to 1.0. So which means if it is not greater than u, then you will choose this input, which means the ith object fully. That's why you are setting x of I. X of I is your output array that will actually give you fractions of input we have taken. Okay, so x of I is equal to 1.0 and u is equal to u minus w of I. Now your capacity will be, you have taken w of I, then your capacity will be u equal to u minus w of I. Okay, then you will choose the next element, then w of I is greater than u, then you will break, otherwise you will fully add it. Okay, w of I is greater than u, then you will break. Otherwise, you will fully add that input. That is x of I will be 1.0 and u equal to u minus w. And when you break out of this loop, you will check if I is less than or equal to n. So somewhere when your w of I is greater than u, you will break from this loop, and there you will check whether I is less than or equal to n. What does that mean? I is less than or equal to n means you haven't taken all the inputs. Okay, so your condition, this condition is true for some input. In that case, you will come here that I is less than or equal to n. In that case, you can then all these are small letters. Then x of I equal to u divided by. So you need to choose the fraction for this input. What will be the fraction? The fraction will be u divided by w of I, which means u is the total weight possible and w of I. Okay, that much fraction will be taken. Okay, then that is stored in x of I. Clear? And if this one is greater than I, that is, if you have taken all this thing, then you will come out of this loop. Only if this will be done, only if I is less than or equal to n, which means the last object, this will be done for the last object where I is less than or equal to n. In that case, x of I, the fraction of that input will be u divided by w of I. Clear? Then what is time complexity of this algorithm? What is time complexity of this algorithm? You have one for loop here, 1 to n, you will do this one, and u equal to n. For I equal to 1 to n, you will do this thing, which means this time is linear, 1 to n. Here it is also 1 to n. These are two loops. So the total time is big of n. Okay, then what else? T of n equal to big of n. What else? Yeah, the first procedure is to sort this in profit, sort profit weight ratio in non-increasing order. Okay, so which means the sorting will take some time, and we know that any efficient sorting algorithm will take minimum of big of n log n time. So the total time will be big of n plus big of n log n. That will actually be big of n log n. Okay, so the time complexity will be that. And if we are not choosing this sorting or we are not considering this sorting means your total time will be big of n. Okay, that's all about the greedy knapsack algorithm.